Hello again. We are talking about section 3.1, increasing and decreasing functions and relative extrema. We have tackled increasing, decreasing, relative extrema, and although I don't care so much about defining this, the first derivative test is our way of determining whether critical points are maxes or mins. We're going to do one additional applied example, so word problem, trying to tackle that. So here we are in an ice cave. Great. So average temperature in degrees Fahrenheit in an ice cave, T hours after midnight, is given by this exciting thing. We're in charge of figuring out at what times was the temperature increasing, decreasing, and then we're told that they light a camp stove, which is warming things up, and we're supposed to infer from temperature, basically, what time the stove got turned on and what time it got turned off. Okay, so as always, when we're looking for relative extrema and we've got a formula, we should be looking for critical points to begin with. So the two places that we are supposed to examine are the derivative equal to 0 or the derivative being undefined. And the majority of the cases that we're interested in are going to fall into this first category, that t prime is equal to 0. Okay, so finding the derivative, we need to use quotient rule. So this is our whole low d high business minus high d low, and square the bottom. So with those smaller derivatives, now we have a derivative of 10t plus 1 would just be 10, and derivative of t squared minus t plus 1 would look like 2t minus 1. So just a little bit of power rule left. Now all the derivatives are tackled, and we're trying to solve this thing set equal to 0. So now we actually have an equation that we're going after. So the denominator is usually not that interesting to us. If this were ever 0, then the whole expression would be undefined. That's a separate conversation, but it's not going to help us make this whole fraction equal to 0. So we're not going to have anything exciting as part of our solving process. It's based off of this bottom part. So one thing you could think about is if we just multiplied this denominator piece over, we'd have 0 times t squared minus t plus 1 all squared, but that's just going to be 0 anyway. And as long as this thing isn't ever undefined, then we're safe at doing that. Okay, so basically we're going to disregard that denominator piece, we're going to multiply it over, and then all we're left with really is just the top. So all this stuff has survived and made it down to our equation. With a little expansion, we get some multiply 10 to everything in there, do some FOIL with these, 20t squared and so on. And then combine like terms. So we're down to t squareds, t's, and a constant. So here factoring is in theory a possibility, but I think quadratic formula is probably the wiser strategy. So this, negative b plus or minus square root, etc. Or using a calculator or Wolfram alpha. But whatever strategy we employ, we'll get a couple of solutions this way. And the things to note basically are that, so this came from solving t prime equals 0. And I've made this claim that this is usually where we're going to find all of our solutions, or at least the vast majority of them. There'll be some special cases. So this whole section basically is asking about t prime undefined. And it's a worthwhile question. That's also where critical points can occur. But it turns out that because that denominator, the t squared minus t plus 1, doesn't have any real solutions. You could check that with quadratic formula. But even if it did, it would be undefined at the exact same place that our original function was undefined. So t prime being undefined when t is undefined isn't really all that useful to us. It's right back to that. You can't be a critical point if you weren't already a point on the graph kind of notion. So little t equals negative 1.15 and little t equals 0.95. Those are the only opportunities that this graph has to change its direction. So this is what we did in our prior example and what we will refer to as the first derivative test. We're using the first derivative to test in between each of these two critical points. And so we have 3 regions to look in basically, and we're going to use those test points to determine whether the graph is rising or falling or whatever. Okay, so it doesn't matter what point we pick, but if we pick something from a value to the left of negative 1.15, we're going to pick -2. Again, I like picking whole numbers because they're easier to compute with, but it doesn't matter. We could have picked -3, -10, anything over on the left side here. So what we come up with is that, but again, the most interesting characteristic of this is simply that it's negative. So what that should imply for us is that t is decreasing on this leftmost interval. Okay, so we're there. We're going to test in this middle region now. And I think a very tempting opportunity is to use the value 0, since that happens to fall between these two numbers. So if we test 0, then we get a slope of 11, which is fine, but really what we care about is the fact that it's positive. So since this derivative is positive in that middle region, then the function's increasing on that interval. Finally, let's test in the far right region, and even though it's pretty close to 0.95, let's test 1, because it does fall into that camp. It doesn't matter how far to the right we are. We could have tested 0.9500001 and still gotten some meaningful information. So plugging this back into the derivative, again, maybe I should stress that this is the derivative function we're plugging into. We're not asking for the height, not asking for big T, we're asking for big T prime. So the slope there was -1, but in particular it's a negative value. So t is decreasing on this final interval. And just from the kind of diagram, you can sort of see it looks like it's going to bottom out at -1.15, and it looks like it's going to top out at 0.95. So it looks like -1.15 will be a relative minimum, and x equals 0.95 will be the location of a relative maximum. So it's increasing between those two things, wherever our arrow is upward, and it's decreasing for all these other values. There's certainly an argument that we wouldn't have all real numbers be the domain of this temperature function, because they're not in the ice cave forever, I'm hoping, and the temperatures wouldn't continue to change at those rates. But just looking at our pretty little graphs here, everywhere there's a down arrow, that's an interval of decrease, and the interval in the middle is our interval of increase. So what this should imply, that we were asked to find increasing and decreasing, it should imply that -1.15 hours from midnight, that is 1.15 hours before midnight, that should, to the nearest minute at least, corresponds to 10:51 p.m. That's when this temperature function started increasing. So that makes sense to say, oh, that's probably when they lit the stove. And then the place where the function starts to decrease, the temperature starts to go down again, is after 0.95 hours, so in other words, right around 12:57 a.m. Then they probably turn the stove off, because that's when the temperature starts to drop off again. And in math terminology, that's the points that correspond to relative extrema. It's really handy to have a graph, though. Sometimes just to look at a picture is, like they say, worth 1,000 words. So this is our temperature function. I would never expect you to graph this by hand, but graphing calculator, Wolfram Alpha, etc. are pretty handy. So we can see temperature sort of decreases up to a point. This is the claim where we have a relative minimum and where the stove is turned on, because the temperature starts to increase at that point, until we get to here. And the claim is there we have a relative maximum, and this maybe corresponds to when the stove is turned off, because the temperature starts to drop off again. Okay, so that's the first derivative test in an applied setting, helping us find relative maxes and mins and intervals of increase and decrease for these functions. That's it for section 3.1. We'll see you for concavity in the next section.